Radioactivity is when a nucleus possesses excess energy and decays, meaning it changes nuclei in some way, to reach a more stable state that has lower energy, usually emitting radiation, that is, some or all of this extra energy, as it decays. Said another way, without all the hair splitting, radioactivity is a condition in which the nuclei of a material are unstable, they decay, and emit radiation. What unit do we use to describe the amount of radioactivity? The modern SI unit is 1 decay per second, or 1 becquerel, abbreviated BQ. Another widely used unit is the curie, equal to 3.7 times 10 to the 10th becquerels. The abbreviation for a curie is CI. A curie is a much more user-friendly unit and is what's used in radiation protection in this country. But everyone else in the world has already moved to the SI units, so I'll try to use both as I go through my lecture here. Once again, we need to put some math to things, so let's scratch our heads and think about how we would go about getting a collection of material that would produce 1 decay per second, for example. Just between you and me, I bet it has something to do with that decay constant we derived earlier, and I also bet it has something to do with how much material is involved some way. By how much material is involved some way, I mean that if we had the same concentration of radioactive atoms in a material, and I had one pile that was twice as big as the other, I expect twice the decays in the bigger pile, right? If we refine our idea of material a little bit, it gets even easier. What we're actually looking for is the number of radioactive atoms. Interestingly enough, the decay rate is not influenced by anything as near as we can tell. The nuclei sit there playing Russian roulette and not talking to any of the other nuclei. Actually, there is one form of decay that we don't talk about here that is influenced by crystal structure. So the decay constants vary a little depending on the material. Once we know the decay constant, the probability of a collection of atoms having a decay is just the number of atoms, N, times the decay constant, lambda. In math, this translates to activity A is equal to N lambda, where A is the activity in decays per second. Let's work an example. Suppose that the half-life of U-235 is 700 million years, and the measured activity is 300 decays per second. How many atoms of U-235 are there? First, we need to convert half-life to the decay constant. Let's see. Oh yeah, we know that lambda is equal to 0.693 divided by the half-life. And after a little thought, we realize that we want the units to be in inverse seconds, not inverse years. Okay, 700 million times 365.24 days per year times 24 hours a day times 360 seconds per hour gives 2.21 times 10 to the 16th seconds. So lambda is equal to 3.14 times 10 to the minus 17th inverse seconds. Well, that's kind of small. So returning to our magic formula, we know the activity A, we know lambda, so we can find the number of U-235 atoms, and it is 9.56 times 10 to the 18th atoms. All right, how much does this weigh? Remember your chemistry? 6.022 times 10 to the 23rd atoms of U-235 weighs roughly 235 grams. So we have 3.73 milligrams of U-235. Even with a huge half-life, there are many atoms per gram, so we still get decays. Finally, let's use one last trick so that we can describe activity as a function of time. Activity is a function of time? Yep, the atoms are decaying away, right? So N is changing. Remember our equation for decay? N equals N naught times e to the minus lambda t. Look what happens if we multiply both sides by lambda. In words, it says the activity is predicted the same way as the remaining nuclides are predicted. No real surprises here. but it's nice when someone shows you.